So let me show you something here. I said I would teach you about the trajectory. A 2D trajectory problem. If you look at my website, dr.c Physics Made Simple YouTube site, you can find videos for a ball being thrown directly up in the air, directly vertically. But in this case, we're going to do something a little different. An archer wants to shoot his arrow as far as possible downrange. That's an interesting point. Not many physics classes actually tell you that answer. So let's do it here. So initially, we have the plus x downrange, plus y is the vertical. Let the arrow be located at some initial height above the ground where the archer is standing. Call that h naught. So then we measure the range as the horizontal distance down. So this arrow is going to be launched with a velocity vector v naught that makes an angle theta with the horizontal. Question is, how far downrange does it go? You can see it's going to go out in a parabolic trajectory, and it's going to return back to the horizontal at this distance. We're asking, what is this? What angle theta is necessary to maximize this range? The range R. Okay, so let's write the initial velocity. The initial velocity vector that's launched here has two components to it. It has a horizontal v0x and has a vertical component v0y. So it's a 2D problem. The arrow goes vertically upward and then back downward, but it also travels in a plus x direction. So v naught vector is equal to v naught x hat plus v naught y hat. If you're not familiar with these basic vectors, go watch my vector videos and shorts so you can get beef up on concept of vectors. All right, so what's the horizontal distance x that it's going to travel? Let this be 0 here. X is, there's no gravity, there's no force in the x direction. It's just traveling at its initial speed. The initial position is x naught equals 0. So the final position, x, the distance x that it travels, is v naught x times the time. The time it takes to travel up to its maximum height, h max. And note here, v is equal to 0, v0y. Sorry, too many subscripts. Sorry about that. Vy, the y component, the vertical component of the velocity, at the max height is 0. That's how you get the max height. That's an important concept to know. And we showed that in the 1D vertical trajectory problem. So I drew t with a twiddle on top. T-twiddle is twice the time that it takes to go to the max height. It takes a time to get to its max height, and then it falls from its max height back down to the horizontal. So T-twiddle is equal to 2t at the top. That's just straightforward. That's equation 2. This is equation 1. So let's compute the time to the top. So the final velocity, Vy, is equal to V naught y minus acceleration of gravity times the time to the top. This is the velocity in the y direction, the y component of the velocity from the launch time up to the top. So we have gravity acting down on the arrow, and it's a minus to show it's down in the minus y direction. So we can solve this for the time to the top. The time to the top is Vy minus V0 y divided by a minus g. But remember, Vy at the top is equal to 0. So T top is equal to V naught y divided by g. Hopefully that's still in the camera. Yes, we can see it. Now what are we going to do? So we know the time to the top, V naught y divided by g. Let me put some initial values here. Let V naught be equal to 100 meters per second. It's about 300 and something feet per second. That is a high performance Bose initial velocity for an arrow that weighs approximately 100 grams or 0.1 kilograms. So let's assume the mass is 0.1 kilograms as well. So let's take this as the initial conditions. So what are we going to do now? Let's compute x in equation 2 using this time from equation 3. So now that we have the time to the top, let's compute the range. So x, using equation 2, is V naught x times the time to the top Let me just substitute it in. V naught x from here, then t twiddle, which is 2t. So I'll put a 2 here, 2t top. But this is equal to 2 v naught x, and t top is over here, v naught y divided by g. Now let's substitute in what the values of v naught x and v naught y are. I wrote it up here. V naught x is equal to v naught cosine theta. V naught y is v naught sine theta, just using the geometry. So this is 2 v naught squared cosine theta sine theta divided by g. So now you can maximize this by just checking values of theta by inspection and find out that the maximum occurs, theta giving the maximum distance x is 45 degrees. You can plot it, you can put it in your calculator, or you can use calculus. I'll show you how to do calculus real quick. Let f of theta be equal to, you're going to maximize this function f of theta, cosine of theta times the sine of theta. To maximize, we take the derivative and set it equal to 0. df of theta d theta. Now let's use the product rule since we have two terms multiplied here. So the derivative of the first term, which is cosine, is a minus sine theta. Now it's times the sine theta, so it gives you a minus sine squared theta plus the first term, cosine theta, times the derivative of the second term, excuse me, derivative of the second term, derivative of sine theta is cosine theta, so this becomes cosine theta squared. We have to set that all equal to 0. So what does that tell us? Sine squared theta is equal to cosine squared theta. That happens when theta is 45 degrees. So you get the same answer directly with calculus. Theta equal 45 degrees. So what is the maximum value? X max, which is going to be 2 times V naught squared times the cosine of 45 degrees times the sine of 45 degrees divided by G. Well, it turns out that the cosine is equal to the sine at 45 degrees of root 2 over 2. Root 2 over 2 squared is 2 over 4, which is 1/2. So the 2's divide out, and you get V naught squared divided by G. That is the maximum value. So let's pause this here and then we'll continue with some details. So let's continue the Archer arrow example. Consider the case, we're considering a specific case where V naught is 100 meters per second. The angle theta is equal to 45 degrees, which we showed is the maximum, gives the maximum range. So we're going to do this numerical example. So let's get the components of the initial velocity. V naught x is equal to V naught cosine 45 degrees, which is equal to V naught root 2 over 2. V naught times 0.707, and that's equal to 70.71 meters per second. V naught y, V naught sine 45 degrees, and that's also equal to 70.71 meters per second. So now we have those components. Let's compute the time it takes to get to the top. So the time to the top we derived earlier is V naught y divided by G. So this is equal to 70.71 meters per second divided by 9.8 meters per second squared, which is equal to 7.215 seconds. So it takes 7.215 seconds to reach the top of the trajectory, and the total time of flight is twice that. Next question is, how high does it go? Well, the height is equal to the initial height, h naught, plus the initial velocity in the y direction times the time, v naught y times t, minus 1/2 gt squared. Gravity's down, so therefore it's a minus sign. We said h naught. H naught is, we didn't define what it is. Doesn't really matter for this case. What we want to solve for is really the height above where the arrow is launched. So h minus h naught is v naught yt minus 1/2 gt squared. So we can plug these values in. 70.71 meters per second times 7.215 seconds minus 1/2 9.8 meters per second squared times the time squared, 7.215 to the top. And when we do this, we get 510.17 minus 255.08, which is equal to 255.1 meters. So that's h minus h naught. It went 255.1 meters high from the launch point. It took 7.215 seconds to get to the top. What else can we say about it? Well, we can do this problem a couple different ways, right? We can get the height to the top a couple different ways. Another way, so this is method 1. We have different equations. We can use method 2. Let's call this method 2 now. We're going to use the expression that doesn't involve the time. Remember, Vy squared is V naught y squared minus 2g h minus h naught. This is the equation that doesn't involve time. We eliminated time. So the initial velocity we know, but when we get to the top, we know that's 0. So this tells us that h minus h naught is equal to v naught y squared divided by 2g. And we can substitute that in. We get 70.71 meters per second for the initial velocity, and we square it, divide by 2, and 9.8 meters per second squared. Computing that gives us 255.1 meters. So that's method 2. Same answer, so it should be. It's just an algebraic difference. Method 3 for computing the height above the launch point is to recognize that the average velocity is given by the change in position divided by the change in time for a constant acceleration, and that the average velocity is the arithmetic mean. So the average velocity is the initial velocity v naught y plus the final velocity that we know is 0 divided by 2. So that's v naught y over 2. And then we use that average velocity, multiply that times the time to get to the top, and that will tell us the height above the launch point, h minus h0. So h minus h0 is v naught y over 2 times t to the top, which is equal to 70.71 meters per second, that's V naught Y, times the time to the top, 7.215 seconds, divided by 2, and that's equal to 255.1 meters. So there we have it, the same answer as method 1 and 2. So we have 3 methods to find the height of the arrow from the launch point.